Okay, I guess I start the introduction. So it's my great honor to introduce our speaker today. Dr. Matthias Rempel is a senior scientist at the High Altitude Observatory of the National Center for Atmospheric Research in Boulder, Colorado. He received his PhD in astrophysics in 2001 from the University of Göttingen, Germany. He has since been working at the High Altitude Observatory, first as a postdoc from 2002 and then as a staff scientist since 2004. Matthias' research area is the theoretical modeling of the solar interior and the solar photosphere. He uses computer models to study key features of the sun, including regions that cannot be directly observed. He led an international team of scientists to create the first ever comprehensive model of sunspots, and his work can help scientists better understand the sun's magnetic fields and the transport of energy from the sun's interior to the solar system. Let's welcome Matthias again and let him start the seminar.
Okay, thank you very much for the invitation to present this talk. I hope you can see the slides now. So what I decided to do here is to give something a little bit like a review, but it is of course a very selective review in the sense that I focus here primarily on work I have been heavily involved with. So I cover MURaM simulations for more, which were done, some of them started more than 10 years ago. And I select here primarily two regions, quiet sun and sunspots, and from sunspots going a little bit in the direction of simulating entire active regions. And I show here on this first slide kind of the range of scales I want to cover in this talk, going really from very detailed convection of small scale magnetism on the sun to the largest simulations we have done so far for active regions, which have a horizontal extent of up to 600 megameters. I end with a very brief outlook on ongoing work, and I won't talk in much detail, for example, about simulations that include the corona, which we have been heavily working on in the recent few years, and other ongoing efforts like treating the chromosphere better and also GPU computing using MURaM. So let's start it with a quiet sun. So quiet sun magnetism. As you know, most of the solar surface is covered by quiet sun at any time of the sunspot cycle. And if you estimate the unsigned flux in the quiet sun, that is something around 10 to the 24 Maxwell. And that is actually comparable to the flux which is emerging in form of sunspots over a solar cycle, more or less, which kind of tells you there's a lot of magnetic energy present in the quiet sun at any time. Why is this really interesting to look at? The quiet sun is pretty much the baseline for any other investigation of the solar photosphere. There seems to be a very strong evidence that the small scale field is independent from the large scale field of the sun, which suggests strongly there is a small scale dynamo operating. And there have been many simulations done in that regard that support this picture. But there are still open questions. Where is the small scale dynamo located? Is this just something which happens in the photosphere, or does it happen everywhere in the convection zone? And really, what are the expected observable signatures? For example, if you look at different scenarios, dynamo action just in the photosphere versus deeper seated dynamo action. And last but not least, the solar photosphere is pretty much the only place in the universe where we can observe a small scale dynamo at work. So just a very brief history of investigations of quiet sun magnetism. I mean, before the year 2000, most quiet sun simulations were hydrodynamic. It really started in the end of 1999 when the first small-scale dynamo simulation, at that time very idealized Boussinesque, no radiation transport, was presented to suggest the idea that magnetic field in the quiet sun may be supported by a small-scale dynamo. And over the years, more and more realistic simulations were introduced. The first one, which really captured all the relevant physics like radiation transport, compressibility, realistic equation of state, was the work by Völkler and Schüssler in 2007. Now, people very quickly looked at these simulations and tried to compare them directly with the available observations. And there were, at least in the early years, quite some discrepancies. Comparison to observations through Zeeman effect kind of suggested these simulations are a factor of 2 to 3 too weak. Early attempts to do Hanle effect forward modeling from these simulations showed an even stronger discrepancy. I mean, it was suggested that one has to scale up these simulations, at least in certain regions of the atmosphere, by more than 12 times to get an agreement. The situation has improved with many more models in recent years, and also this agreement between observations, different simulations has improved, and most recent results suggest that the best agreement is kind of found for vertical field strengths at optical depth unity somewhere in the range of 60 to 80 Gauss. And this is now the case for both Zeeman effect and Hanle effect. Both of them require forward modeling that you account properly for the cancellation you have in the Zeeman effect. And of course, Hanle effect is even more computationally challenging. And I show here on the right just a few distribution functions which were derived through Zeeman effect forward modeling. The red line shows actually distribution of magnetic field as seen in Hinode, and there's the different crosses here are the forward modeled Zeeman signatures from simulations degraded to Hinode observations and analyzed exactly the same way as Hinode data was analyzed. And here it was found that there is a fairly good agreement when you're in the 60 to 80 Gauss range. Now, what changed on the model side to actually get to this point? Primarily higher resolution, less diffusive codes, but most importantly, a different bottom boundary condition. I will talk about that a little bit more. The macro physics are pretty well captured in these photospheric simulations, but there are remaining challenges. And it really comes down to what is the role of recirculation? Because all these domains are very close to the surface, so they have a bottom boundary, which is then coupling essentially the photosphere to the rest of the convection zone. And you have to make assumptions about this boundary. The other challenge is, of course, that we cannot yet realize really a low magnetic Prandtl number regime. The magnetic Prandtl number on the sun in the photosphere is about 10 to the minus 5. Okay. So I show here example of one of those simulations which have been in detail compared to both Zeeman and Hanle measurements. This one saturates at the field strength about 80 Gauss at tau equal 1 in the photosphere. And the bottom panels here show the vertical velocity and the magnetic field strength. And you can see here there is a lot of overturning convection. You see a lot of plasma leaving the domain, and this has to be replaced by plasma which is entering the domain through the bottom boundary. And you have to make some assumptions about what are the magnetic properties in this boundary condition. And that is essentially assumptions about how is the photosphere coupled to the rest of the magnetized convection zone. And the level of field strength you reach in the photosphere depends on this assumption. Here in the right panel, I show different simulations which use different boundary conditions. And there are kind of two groups of simulations here. The orange and red line corresponds to simulations which did have a boundary which either did not allow for a pointing flux across the bottom boundary or just set the magnetic field to 0 in inflow regions. This is the most conservative boundary condition you can do. Then the RMS field strengths in the other simulations, these are simulations which do have deeper recirculation, either by actually closing the bottom boundary, which would be here the blue run, or by actually allowing for the presence of horizontal field in inflow regions. And they typically end up in a regime where the field strength is about a factor of 2 larger. And this does not depend on how deep you make your domain. And that is which I show here on the left panel. The more shallow simulations I show on the right are going down to a little bit over 2 megameters deep. And I have here a second class of models which goes to 6 megameters. And then there's a third class of models which go 20 megameters deep. And you do see the same dependence on the boundary conditions in all of them. And all this pretty much tells you is that the convection zone isn't really a bottomless pit. It has a bottom boundary somewhere, and everything which goes down has to come back up. So you do have a mode of larger scale recirculation in these sort of small scale dynamos as well. Now, can you actually distinguish these two modes of recirculation, shallow, which is just upflow, downflow mixing in the photosphere, from this deeper recirculation? And one way to do this is, for example, looking in so-called exploding granules. These are granules which grow so large that they have to form a new downflow lane in their center. And when you look at the amplification of magnetic field, you see two things happening here. You first see a rather coherent magnetic sheet forming, and then you see some boiling up of much more turbulent plasma on the side. Now, this coherent sheet, that is due to this deep recirculation, because the deep recirculation to the expansion of field in upflow regions ends up in a very smooth seed field, which is then amplified into the sheets. Whereas an upflow downflow mixing at the edge of these newly forming downflow lane leads to this shallow recirculation. And you can see this if you actually look at cross sections. I show here some vertical cross sections through this region where the new downflow lane was forming. You see that there is actually a shallow recirculation where these amplified flux sheet gets wrapped into a horizontal vortex lane, and turbulent feed is brought back up into the photosphere. So you do have these two modes of recirculation present, and you can in principle distinguish them if you have high resolution observations of the photosphere. And here I compare two dynamos where I just changed the bottom boundary to disable the deep recirculation, which is here the bottom two panels. The top one is a model which has the deep recirculation. You see that these more sheet-like strong sheets of magnetic fields that disappear if you only have the local recirculation. You're much more dominated by just small-scale turbulent field. And there are much larger areas really in the granules where the field strength is really close to zero, whereas with deep recirculation, you normally don't find them to that degree. In order to see this turbulent field which boils up from the shallow recirculation, you really have to look deep into the photosphere. I just show here the magnetic field strength of the vertical magnetic field on the warped tau equal 1, 0.1 and 0.01 surface, and you really see these turbulent field from the shallow recirculation really only in the deepest parts of the photosphere. It doesn't make it very far, since it very quickly gets swept back into the downflow lane and disappears again. So this is something one can likely investigate with DKIS in the future, but it's critical to look deep. So one likely has to look at observations near the opacity minimum. Of course, you lose some resolution by going to the longer wavelengths, but you won't be able to see it if you stay anywhere higher in the photosphere. A few words about the energetics of the dynamo. I show here a few terms from the energy equation evaluated for such a high resolution MHD simulation of just the surface layers. Convection is driven by pressure buoyancy driving, which is the blue solid line in these plots. Most of this driving goes into acceleration of downflows, which show up in this energy balance as the negative divergence of the kinetic energy flux, which is the blue dotted line. If you add the two together, you get the black line, which gives you the total amount of energy which is available to kind of drive anything else, like a dynamo or just drive turbulence. And for having the system in a balanced state, in the end, all this driving, which is here in this black line, has to be eventually dissipated through viscous dissipation or resistive dissipation if there's a dynamo. And I compare here two dynamo simulations which differ in their magnetic Prandtl number. And for completeness, I should mention this is a numerical magnetic Prandtl number. These are kind of large eddy simulations. So it's all based on numerical diffusivities, which were a little bit skewed to different Prandtl number regimes. But what you do see in these simulations is that the amount of energy which is essentially converted by the dynamo depends on the Prandtl number. And this is the sorry, I pressed the wrong button. This is the red curve here, which is the negative of the Lorentz force work. And interestingly, if you go to a low Prandtl number regime, you actually end up with the more efficient dynamo in terms of the energy conversion. And this is only a Prandtl number of about 0.01. The sun should be at 10 to the minus 5. So you can expect that likely this small scale dynamo pretty much converts all the available energy which is here in this black line. Of course, it's eventually, if you lower the Prandtl number so much that your magnetic Reynolds number becomes too low to actually keep a dynamo alive, then the scaling will break down. But under the assumption that we are still in the regime on the sun where the dynamo survives even at low Prandtl number, you end up with a very efficient small-scale dynamo in the low Prandtl number regime. You can estimate what is the total amount of energy which goes into the dynamo, and that's about 150 ergs per cubic centimeter at second. If you integrate this over the entire solar surface, just for these 1.5 top megameters of the convection zone I'm showing here, you actually end up with something like 30% of the solar luminosity, which is used to maintain the small-scale field in the photosphere. This is a large number. If you go even deeper in the convection zone, that number might even exceed the solar luminosity, which sounds kind of, I mean, you wouldn't expect that this is happening, but keep in mind, this is not the true sink. The energy is not lost. It's just the energy is eventually dissipated and added back into the internal energy of the plasma, which then can again, through convective instability, drive convection. If you wouldn't have the dynamo, it would be just a viscous dissipation, which dissipates the equivalent amount of energy. But having this rather efficient dynamo raises the question whether it has some other consequences for the system as a whole. And there are a couple of simulations which strongly suggest this. And I just highlight one very recent one here by Hideyuki Hotta and Kanya Kusano, just published just a few months ago, where they conducted simulations of the whole convection zone in a spherical shell at 3 different resolutions. And all these simulations, they have a small-scale dynamo present. In principle, they can also have a large-scale dynamo, but at least in this work, they didn't really find a dynamo which produced a substantial amount of large-scale feed. So it's primarily a small-scale dynamo just existing in the entire convection zone. And what they found is that when they go to higher and higher resolution, that the system leads to more and more solar-like differential rotation, which is shown here in the panel I highlight here. Now, they also did one simulation which they performed exactly the same resolution, but without the dynamo. In that case, they ended up in the typical, more close to Taylor-Proudman state and actually fast rotating pole. So the magnetic field plays a really critical role in maintaining differential rotation in this simulation. But it does one other interesting thing, and this is shown in terms of these power spectra of magnetic energy and kinetic energy. Now, in all these simulations, regardless of the resolution, you always find a regime on the smaller scales where the magnetic energy dominates, which is in the super-equipartition state. As you go to larger scales, in the low resolution case, eventually you end up in a sub-equipartition regime where the kinetic energy dominates. But what they found is that their system made a transition where even on the larger scales, the system suppresses the kinetic energy to the point that it pretty much is equipartition throughout the system, and then super-equipartition on the smaller scales. And they found that the peak of kinetic energy shifts from wave numbers of 6 to about L equal 30. And Many of you, of course, know that we have this problem called the convective conundrum on the sun, that there seems to be too much power on large scales in many simulations. And this simulation is suggestive that perhaps the small-scale dynamo may play a critical role in actually resolving this issue. And this is a movie taken from their paper, which shows the vertical velocity, also indicative of the differential rotation present, and the magnetic field. And you can see here it's predominantly a small-scale magnetic field throughout the domain. Now, one other aspect of the small-scale dynamo I quickly would like to touch on here is the origin of the quiet sun network field. This is taken from a paper published by Bruce Lights in 2008 about the solar minimum around 2006, a deep saturated scan with Synode. And what you see here is that actually the quiet sun has a lot of network feed as well. I mean, it balances out eventually, but it's a mixed polarity network, but there's a large scale field. Does this have anything to do with a small scale dynamo, or does it have a different origin? Now, when you look at these MHD simulations, you might get the impression that these MHD simulations would not be able to maintain a network field like this. And I show here two simulations. So let's start with the bottom left panel. This is a simulation which was done in a box 9 by 9 megameters wide. As the typical setup, there is no net flux in here. The magnetic field, the flux is balanced. If you just expand these boxes to larger scales, of course, to fill a large domain, you would not see any network feed by construction, because in each of these boxes, there is no net flux in there. However, if you do the other experiment, that you actually start with a small-scale dynamo simulation in a large domain, which also goes deeper, in this case 20 megameters, you end up with a network feed, which I show here in panel B on the top right. And then I show here in the top left panel again, just a 9 by 9 megameter subsection. You do see here some differences in detail that has to do in part with the fact that, of course, these larger scale simulation was done at a lower resolution. And of course, the other effect is if you just randomly pick any 9 by 9 megameter subregion, that won't have a balanced flux. And that's the reason why also in these 9 by 9 cutout, you see some stronger indications of network feed, which wouldn't be there if you just set it up as we typically set up small scale dynamo simulation in a smaller box. So the bottom line is here really that having a network field is part of the small scale dynamo, at least if you allow for enough stratification in the domain. And as usual in my talk, I have also a quiz for you. I show here two magnetograms. One is actually the real sun, one is the simulation, and I let you decide which one is which. Another question which has been asked and is critical to this idea of having a small scale dynamo is, does a small scale dynamo actually vary with the solar cycle? And I show here two results which perhaps contradict each other a little bit. There is this result by Bühler in 2013 based on Hinode data, where they could not find a systematic trend. I mean, there's some scatter in the signal they can find at a given time, but there is no systematic trend in the strength of the quiet sun field with the solar cycle, which is indicated here by the triple dotted dashed line in the background. Now, there are other results like this paper from 2018, which was based on MDI data. You might argue MDI is perhaps not the most accurate instrument to really look at the quiet sun, but at least they made the claim that over longer times, there is a systematic variation of the quiet sun with the cycle. And they also argued that the result is consistent with the result by Bühler if they restrict the analysis to these shorter timescales. So obviously what we need here is having the work by Bühler repeated for the full amount of data we have available from Hinode. But I want to attack this from a different angle and really ask the question, can we actually use the total solar irradiance to constrain quiet sun variation with the solar cycle? And in order to do this, what I did here is I used quiet sun simulations to estimate the TSI sensitivity to the quiet sun field strength. So what I did here is setting up dynamo simulations and the 100 Gauss network case by varying the feed strengths, taking advantage of the dependence on the bottom boundary, and then all these simulations have relative transfer, so you can compute the total outgoing radiative energy flux and use this as proxy for the total solar irradiance. If you now plot this as function of the field strengths, you see a more or less linear relationship. Interestingly, the network case pretty much has the same dependency on field strength as suggested from these three quiet sun cases. So whether you have a net flux imbalance or not, it seems to be a secondary effect here. The slope of this curve tells you the TSI sensitivity, and that is about a 0.14% increase for each 10 Gauss of mean vertical field strength at tau equal 1. And what this really means is, if the quiet sun would vary a significant fraction, something like 10%, it really would make a dominant contribution to the TSI we observe. And I show here a TSI measurement from a recent paper, and the arrow I put you on the side kind of gives you an idea. If the quiet sun would vary by 10% with this TSI sensitivity the simulation suggests, then just the quiet sun alone would account for most of these TSI variation. Now, the current understanding is that, of course, most of these TSI variation is due to the contribution from active regions, particularly plush regions. So one can pretty much, I think, use this as an argument to put really strong constraints on how much the quiet sun could possibly vary during a regular solar cycle. Now, with this, I now move on to modeling of sunspot fine structure. And this is really a very condensed slide, which shows you a lot of progress over more than 15 years. And I tried to put most of these simulations on here roughly to scale, starting with the original work by Schüssler and Vögler, focusing on the umbra and establishing for the first time that umbra dots actually are of magnetoconvective origin in terms of overturning convection. Then there have been a couple of these lab simulations to understand the umbra-penumbra transition until we were able to do full sunspot simulations a little bit more than 10 years ago. And this really was possible because over this time, really the available computing power increased dramatically, more than a factor of 1,000. So simulations could very quickly scale up. So what has been found in the simulations is pretty much a unified magnetoconvective picture of magnetoconvection from umbra dots to penumbral filaments and also light bridges. These simulations show that penumbral filaments are regions where you have moderate enhancement of the horizontal field strengths, a strong reduction of the vertical field strengths, leading to these fingers of more or less horizontal feed embedded in the background feed, which is more vertical. You have strong outflows reaching speeds of 9 kilometers per second around tau equal 1. And the underlying magnetoconvection mode is overturning convection, which due to the presence of magnetic field is anisotropic. Now, the reason we do these simulations, of course, is that we can also look at cross sections. And then what you find here is that these penumbral filaments, the cross-section really is a little bit more structured. It's not just something like a horizontal flux tube. If you look here in detail on the radial magnetic field, what you see nicely in these penumbral filaments is that they have this boundary layer where you have a actually enhanced horizontal field strength whereas the vertical field strength is reduced. At the same time, you still have a core of vertical field, which is a little bit stronger. And so what you end up with is really a structure where only the outer shell shows these mostly horizontal field. In the core, the field is still a little bit vertical. And the evershed outflows are really limited to the top of the domain around optical depth, equal unity, and they very quickly fall off this height and then even change sign further up. Now, interestingly, you can actually derive from these simulations by just evaluating the force balance and throw out all the terms which don't seem to be very strong. You can end up with very simple force balances. In the vertical direction in these filaments, on average, you just have a close to magnetohydrostatic equilibrium. And in the horizontal direction, you end up with a component of the Lorentz force, which has to be balanced by acceleration forces. And the acceleration force is here actually the vertical, the advective term from the vertical transport of horizontal momentum. And so in some sense, you need the evershed flow to complete the force balance in these penumbral filaments. You can go a little bit further and kind of evaluate. In order to maintain this for a longer time scale, you kind of need to confine this boundary layer, and you end up with a condition that the vertical magnetic field strength, the vertical flow velocity has to exceed the vertical FM velocity, the FM velocity computed with the vertical field strength. And then you can derive from this that the horizontal outflows you expect from this have roughly a phenic velocity with respect to the horizontal field strength. And this is what you see here. These are maps of the velocity relative to the components of the FM velocity just computed with vertical and horizontal field. And you see that the evershed outflow at optical depth unity is really very close to FM velocity really throughout, whereas the vertical velocity exceeds the FM velocity in several locations. And another important takeaway is really, if you have magnetoconvection, this really implies reconnection and emergence and submergence of field. You do not just have flows along field lines. And one way to quickly see this is if you show magnetic field lines of these regions which do have strong outflows in the penumbra at different locations, you actually see that you find strong outflows regardless of what the field connectivity is. You find them on field lines which connect to the top boundary, and you find them on field lines which actually turn over back into the convection zone. And what this really tells you is you have a situation where certainly the flow is strongly aligned with the field for a certain amount of length, but eventually you have motions across field lines, and actually a significant fraction of the mass flux returns in regions in the penumbra where the magnetic field is still pointing up. So it actually returns to the submergence of field lines. So the mass eventually decouples also from field lines through reconnection, as it happens constantly in the photosphere. And you do see that there is a substantial misalignment actually between field and flow if you look at these in the downflow regions. In the upflow regions, in the center of filaments, field and flow in general are much more aligned. These simulations were also able to show some further fine structure of filaments, like these striations or twisting motions, which lead in the intensity. If you do time slices of the intensity to this fishbone type picture, they have been originally found in Hinode, and we later found them also in these simulations. And what they seem to be is really a flow instability where the central upflow in these filaments has an instability in the sense that it's periodically swaying to the side and essentially draining the mass to the left, to the right side of the filament periodically. And this leads to this fishbone structure in the intensity. Now, this doesn't show up in all filaments, but at least we're able to identify a few examples where that is the case. More recent work focused also on the structure of light bridges. This was a flux emergence simulation performed by Mark Chung, and Shin Toriumi looked at a light bridge which was forming in these flux emergence simulation naturally. And I think this is one of these very lucky cases where you just by chance end up with the Hinode observations, which almost looks identical to the feature you found in your simulation. The only difference is that the horizontal extent in the Hinode observation was twice as large as in the simulation. But otherwise, it did really a nice side-by-side comparison of many quantities, found a lot of similarity. And if you look at the overall structure of in flow structure, magnetic field structure in the slide bridge, it actually doesn't look too different from what you typically find in penumbral filaments. The only difference was that here is a bidirectional horizontal flow diverging from the central part in the light bridge, whereas penumbral filaments typically have a preferred direction, the Evershed flow. Now, in spite of all these great success, there's still one nagging issue with these simulations, which is really the role of the top boundary condition, which hasn't been resolved. I mean, all these pretty simulations which show very extended penumbrae, they all have in common that the top boundary condition in simulation forces magnetic field, which is more horizontal than what you would get from a potential field. And there were a lot of different reasons why this could be the case, but none of them really turned out to be so far a really fruitful way to resolve this issue. It was not the limitation of periodic domains, since the same issue happens in much larger domains. There seems to be some precursors in some observations where penumbra seems to be first visible in the chromosphere, which certainly indicates that there might be something pressing down from above. But there are also some recent analysis I show on the next slide, which kind of shows that this is likely not the case. Turbulent pumping was suggested. It's certainly present in these simulations, and you see a lot of opposite polarity flux at the edge of these sunspots, but at least so far, it doesn't look like that is enough to keep the penumbra alive, and there was no significant resolution dependence. Another suggestion is that the sunspots subsurface field structure is really the crucial point here. And this was first brought up by Åke Nordlund a couple of years ago. He suggested if you have these sunspots much more concentrated, which causes the field to fan out more, that this might help to produce a penumbra. There has been some recent work on this I would like to show, which maybe at least strengthens the case that we have to look more carefully on the subsurface structure. Let's first talk about the top boundary issue and the Urja criterion. So it has been found that there seems to be magnetic field strength of about 1,800 Gauss, which seems to nicely kind of mark the boundary between umbra and penumbra. Now, this has been somewhat questioned in recent works that is perhaps less universal, and there is some dependence on the spot side as well. But I think all these works, they kind of found something in the range of 1,600 to 1,800 Gauss. Now, the problem is that the sunspot simulations, and this is actually a simulation here, which was just analyzed like Hinode and degraded to Hinode. In this case, shows that this field strength is about 1.3 kilogauss, at least if you use this boundary condition where the field is artificially made more horizontal to get a more extended penumbra. If you use a potential field, you don't really have a great penumbra, but you have a magnetic field strength at this umbra-penumbra boundary, which is more similar to what you found typically in sunspots. So at least there is some indication here that the sun is not playing this trick we are playing with our simulations at the top boundary. And recently, there was also some discussion if perhaps this magnetic field strength is related to the Gough-Taylor instability, which is a generalization of the Schwarzschild criterion in the presence of vertical magnetic field. There has been some analysis of sunspot simulations in this regard by Markus Schwassmann in recent years, which indicate that the stability criterion pretty much, I mean, is consistent with it's pretty much stable in the umbra, and then if you're in the penumbra, it no longer suggests stability. So there is at least some possible theoretical explanation for having some clear field strengths to mark the umbra-penumbra boundary. Now, coming to the role of subsurface field structures, there has been this recent work by Mario Pagna, who just did his PhD a year ago on this at the Max Planck Institute for Solar System Research. And he looked at sunspot simulations set up in a way to control the fluting instability of the subsurface magnetic field structure by essentially changing the curvature of field. And what they found is if you make simulations more fluting unstable, you get more of these fingers of feed-free plasma entering from the convection zone. And this can help to get more penumbra filaments. But it's also a fine balance, because eventually this fluting, if you do it here in full 3D sunspot simulations, will develop to the point where it really starts taking the sunspot apart, and it transitions really the individual penumbra filament more to something which looks more like light bridges. So there's still kind of this issue that you have to come up with a very delicate setup. You want to have some fluting instability, but you also want to have it to stop at some point to keep the sunspot actually stable. It's still, I think, an open question, really. It doesn't fully resolve the issue, but at least it tells you that the subsurface field structure deserves a very careful look. Now I would move on to even larger scales. Now this is a simulation which was also done about a little bit over 5 years ago, which is large enough to actually include the mode region of sunspots. And you can see here, if you look at the magnetogram, synthetic magnetogram, or if you look also at the cross-section down here showing the vertical velocity and field strength, that the sunspot is indeed surrounded by a mode cell with outflows on the order of 500 meters per second, as you find it on the sun as well. This again shows just a map of photospheric properties. One thing I just want to highlight here, that this simulation also showed one other feature, that sections of the penumbra, at least for times of a few hours, showed counter-evershed flows. And more detailed analysis showed that these flows can be actually explained by siphon flows. And there seems to be kind of a bistable situation where sometimes the system transitions into a counter-evershed flow regime, but then after a few hours transitions back to the ordinary evershed outflow regime. And some behavior like this has been also found in observations. But what I really want to show here is that in this setup, I did an experiment where I actually turned the sunspot into a naked spot by taking advantage of the dependence in the top boundary condition. So I can actually remove the penumbra at least and decrease the penumbra extent substantially by playing this trick with the top boundary. And what really happens then is that the evershed flow, which is here shown in the panel E, goes pretty much away. You still have a few filaments which have outflows, but it's dominated by an inflow towards the naked spot in this case. Interesting thing is both spots have mode flows, which is shown here in the top panel. Naked spot is red, the sunspot is blue. And the other interesting thing is if you shift the sunspot to the left, so that actually the outer edge of the spot in both cases, naked spot, sunspot, are in the same position, you actually see that the flow profiles in the mode region pretty much add up to each other and look very similar. And this is something which also has been found in recent work, which suggests that the extent of the mode flow region is pretty much something like the spot boundary plus 10 megameters. It's not exactly something like 2 times the spot boundary as it was suggested by earlier simulations. Now, of course, the mode region is also defined through enhanced mixed polarity field that perhaps extends a little bit further. Don't go too much into detail here, just want to mention that it's a more complicated picture. It seems to be a magnetoconvection mode, really submergence of horizontal field from the magnetic canopy plus re-emergence. Very often the flux balance of the mode region is analyzed by just looking at the radial transport of vertical field, but at least what you see in simulations is that also the vertical transport of radial field has a strong contribution. And actually, the contribution of both of them adds up to almost zero, and it's only a fine imbalance between the terms which really matters in the end. Another interesting aspect which these simulations showed is this question about thermal structure in the mode region, and this question, do sunspots actually have a bright ring? And I show this here in the right panel, which shows the average temperature in the mode region underneath the sunspot, about 4 megameters depth, by just doing a average in time and also a spatial smoothing. And you indeed see that sunspots are surrounded by a hot ring. Now, if you just look into an individual snapshot and just look at the temperature, you actually see that there isn't really an enhancement of temperature at all if you just compare the temperature of upflows in the mode region to the temperature upflows anywhere else in the convection zone. But what really happens here is that you have a lower filling factor, downflow filling factor in here. So you have much less cool downflowing plasmas. That enhances the average temperature. But the temperature in upflow regions, the entropy in upflow regions is the same as anywhere else in the convection zone. And this means when this plasma finally enters the photosphere surrounding the sunspot, it leads to a photosphere which has the same brightness as the photosphere has anywhere else. So this is kind of a sneaky way nature finds here to actually have a hot ring around sunspots without having a bright ring in the photosphere. Other recent analysis was here done by Hanna Strecker, looking at actually the fluting instability in the sunspot. And what she found is there is an indication that the sunspot becomes over time more and more corrugated, and she translated this corrugation into essentially estimating how fluting unstable the sunspot is as function of depth, and she found that this is pretty much consistent with the original idea suggested by Meyer et al., that you have a fluting unstable sunspot throughout most of the convection zone, except for the uppermost 4 megameters, where the buoyancy of penumbra stabilizes the spot. Now, the interesting thing is that the sunspot didn't really decay in terms of flux, which had to do with stabilizing effect from the mode cell. At least for the 100 hours the simulation ran at that time. The naked spot simulation I did when I investigated the mode flow, that one actually did show a steady decay, since, I mean, while the mode flow was present, it allowed for more flux to escape through submergence of flux, since there were a little bit larger downflow filling factor present in the mode region of the naked spot compared to the fully developed sunspot. Okay, and with that, I would like to transition to the last few slides where I want to show some of the recent full active region scale simulations I have been doing. This is an ongoing NASA LWS effort, which is led by Doug Brown. And what we really try to do here is simulating active regions which reflects the feed distribution of observed active regions. And the idea is really to perform a helioseismic flow measurements on these simulations and quantify the effect of strong magnetic field, which is present in the active regions, on these flow measurement. The approach I took here to initialize the simulations is that I start with an HMI magnetogram, and I do feed extrapolations both upward and downward. It's a potential feed extrapolation going upward. Downward, it is something like an inverse potential feed extrapolation, but that is, of course, notoriously unstable, since potential field extrapolation is a smoothing operation. So inverse is the opposite of smoothing. So I combined this with a low-pass filtering to keep it stable, and that allowed me to kind of have a trunk-like subsurface feed structure in there, which reflects a little bit what you likely expect from a sunspot, of course, but this is ambiguous. We don't really have good constraints on what the feed structure should be. After this initialization, these simulations are free running, so they can derail from the sun as they wish. But since you're dealing with very large scales, until the magnetic field distribution really derails from the sun, it takes quite some time. And we have been running these simulations for up to 100 hours. Now, these shows now flow maps measured and computed through helioseismic analysis. This was done by Doug Brown. So one way to measure actually these flows is to take the vertical velocity at the top boundary and do the helioseismic inversion of the P modes, F modes you observe. The other way is you just take the 3D velocity field and you forward model what would be the estimated travel time shifts, north, south, west, east, inward, outward propagating. And this is shown here in these panels. And what they actually show is now the difference between the measured flows through helioseismic methods and the modeled flows, what you would expect if, standard assumptions which do not take into account the presence of magnetic field are valid. And what you do see here is that it works pretty well everywhere, except when you really get to the strong sunspots. And it really depends strongly on field strength. As you can see that here in this case, the leading spot, which is more coherent, really leaves a very clear difference here in the comparison between modeled and measured flow, whereas the trailing spot, which in this case was more diffuse, does not show the signature. And you do similar patterns in simulations we have done for different active regions or repeating the same active regions with slightly different magnetic field structure. But in this case, you see that there was a pore forming in the trailing spot region, which actually had the signature. So it shows nicely kind of what is the field strength you have to worry about in these measurements and when are the signatures significantly weak. Okay, this is my last slide, just really very briefly mentioning a few ongoing efforts and future work. But we have been heavily working on extending MURaM into the corona. This is the work I have been mostly involved in the last 5 years or so, and we have used these extended MURaM code for flare simulations. I show here one example of a recent simulation which is done in collaboration with Georges Chinsoglu and Mark Chung, where we set 2 spots on a collision course to trigger a flare. So this is actually, it's the strongest flare we have simulated so far with MURaM. It's, if you compute the Gauss X-ray flux, it would be M1 flare. It released about 2 times 10 to the 31 ergs. Other work which is ongoing, and this is really work which is led by the Max Planck Institute for Solar System Research, is really now the chromospheric extension of the MURaM code, implementing NLTE very much along the lines of the recipes which have been demonstrated in Bifrost before, and also some computationally efficient ways of dealing with ambipolar diffusion and Hall effect. Another effort I just want to mention here, but we have been heavily working on in the last 3 to 4 years, is a GPU refactoring of the code. This is a collaboration between NCAR, Computer Science Department at the University of Delaware, the MPS, and Lockheed Martin. And we are now at the point where we have a really very close to production-ready code which can run on GPUs. We used OpenACC for the refactoring. The code performance is about that a single GPU is roughly as fast as 100 CPU cores. So if you take the typical supercomputer with GPUs, they have typically something like 4 GPUs on a node versus about something like 40 GPUs. What you really get is roughly a 10 times speed up on a per node basis you're using. And so far, the GPU code has been tested scaling up to 100 GPUs, but more should be possible. We had found a few bottlenecks we have removed since then. So in principle, scaling to more GPUs should be possible. That brings me to the end of this talks. Just a few takeaway points, since I really covered a lot of ground here. One main takeaway really is, I think we really have to understand very well the contribution from small-scale magnetic field. It seems to play a very critical role for understanding the convection zone dynamics in general, including difference rotation, convective power on large scales, and even perhaps the large-scale dynamo. sunspot simulations, as pretty as they look, there's still this nagging issue, which hasn't been resolved, is that you only get a really decent penumbra if you use very tailored setups, either in terms of boundary conditions, which are not always physical, or fine-tuning the subsurface structure. This is a little bit at odds with the fact that on the sun, sunspots really don't have any issue forming penumbras. You don't see that many failed sunspots in that regard. So at least on the sun, it seems to be a very robust process in the simulations. Something is still missing, and there are a few candidates for solutions, but I don't really know that there's really something like a smoking gun where we could agree on this really resolves the issue. Large-scale active region simulations, including corona, are computationally feasible now. It doesn't mean they are cheap, but they can be done, and much more will be possible in the future if you really push the limits by using GPUs, as we are heavily working on. Thank you very much.
Thank you so much, Matthias. That was great. Before we open it up to questions really quickly, can you go back to your small scale dynamo quiz? I set up a poll.
Okay.
I want to see what people think about whether the left or the right is observations.
Okay, let me.
All right, I'm gonna open a poll and you should be prompted to put in what you think.
Is that a quiz?
Yeah, so which one is the simulation and which is the observation? And it's anonymous, so don't worry, no one will know if you get it wrong. Matthias, I'm assuming you know which one's which?
Yes.
All right, it seems like a couple more coming in. It's pretty even, but it looks like more people think that the left is the observation and the right is the simulation. Can you give us the answer?
Yeah, and that's correct. And you can kind of, oh, sorry, I pressed the wrong button. Where was it? So you can kind of tell it, you see a little bit more finer structure here in the right, which is why this is a simulation, but you can also tell, look at this pattern I showed before. Let me see, I cannot advance my slides right now. Yeah, I showed this Hinode map. What I did is I cut out the region here, the left part of this panel. You kind of see this large scale pattern here. That is the one I showed here. This is the one you do see here. Yeah.
Thanks. All right, we can open it up to questions now. Riju, do you want to take over?
Life has raised hands.
Yeah, Matthias, can you compute the so-called open flux? And if you can, how does that match what we observe?
I mean, in some sense, in the simulations, I mean, I guess in terms of open flux, you're referring perhaps in the sun, what you would see in corona holes or so. I mean, these are not simulations which cover really the sun on that scale. So in some sense, you know exactly, in some sense, what the open flux simulation box is, since you know what the flux imbalance is. So I'm not 100% sure I fully understand your question.
Well, I will go one step further. The flux in the photosphere, most of that, I think, returns to the photosphere. So you can probably,
yes.
Yeah. And so the question is, there's a certain fraction that does not return, and if you can have a handle on that.
I mean, certainly in the simulations, we know exactly what that fraction is, because, I mean, you have no trouble computing in there. The interesting question is doing the experiment through forward modeling. If you try to derive that open flux from a simulation, after computing synthetic observations, how close is it to what you actually would derive on the sun?
Okay, thanks.
Before we calling Alberto, who also raised hands, we have two questions in the chat. They came first. So maybe Amy, do you want to repeat your question in the chat?
Well, I think it might be redundant. I mean, I guess when you were talking about the recirculation of the field, I was just curious whether the recirculation that you were including was actually sort of an observed or an estimation of how much field you thought did get recirculated, or whether, you know, so whether you were using an estimation of how much flux was removed from the photosphere by eruptions higher up, or whether it was just necessary to include the recirculation to get the convection zone energetics correct.
So essentially, so the recirculation is not directly measurable, I would say, because it's really something which happens beneath the photosphere. But the observable, which strongly links to this, is what is really the saturation feed strengths you get for the quiet sun. And there, if you do not account for this deeper recirculation, you end up with dynamo oscillations where the mean vertical feed strength at tau equal 1 is around 30 Gauss. And that is a little bit more than a factor of 2 weaker than what is inferred from both Seemann and Harlan measurements. So indirectly, I can kind of tune up this amount of recirculation until I hit this observed value for the quiet sun feed strength. And this is essentially what has been done in these simulations. Now, interestingly, it doesn't really matter too much how you implement this recirculation. I did the experiment of both using a closed boundary, which just forces all the plasma to recirculate. In that case, I just add a little bit heating at the bottom boundary to put in the energy, which is lost through radiation in the photosphere. Or if you just keep the bottom boundary open, as we usually do, and just allow for the presence of horizontal field, both lead to very similar solutions in the end. So indirectly, you can constrain the amount of recirculation you need by just looking at what is actually the feed strength of the quiet sun. And you need a large amount of recirculation to actually match that value which is observed.
Okay, thanks.
Todd, do you want to repeat your question in the chat?
Sure, I can read it for you. Thanks. I think great talk. You know, COFFIES is particularly focused on the interior of the sun and how to make the links between that and the surface. And so I thought the bottom boundary of your, you know, particularly in the quiet sun, but, you know, following on from what Amy was talking to, and in the stronger sunspot regions, the field strength, what can we do to make closer links? I mean, is there anything about the near surface shear layer, or, you know, things that are a little bit deeper? What's the approach for making a better connection or a better modeling for what's happening a little bit lower down, and linking that to your modeling of the nearer surface?
I mean, on the modeling side, really, I think while these are still big simulations, I mean, we're getting to the point where we actually can do full convection zone simulations. And really the one person who is pushing the limit hard is Hideyuki Hotta. And he actually has done by now full convection zone simulations going all the way to the base of the convection zone. So doing that all in one coherent go. Of course, his full convection zone simulations are not yet global. I mean, he has also done a full photosphere simulation, but that didn't go that deep. But certainly one way to link it is actually by, instead of having separate models for the deeper layers and the surface layers, doing it in a consistent way all together. Now, with respect to observations, I mean, you bring up the near surface shear layer. I mean, there has been some work in simulations trying to understand that in terms of the angular momentum transport you get in these simulations. And there was some mixed success in getting really a near surface shear layer in these full 3D approaches. At least the one I have been involved with, which was also done by Hideyuki Hotta, he was able to get some indication of a near surface shear layer, but that at that time was a purely hydrodynamic simulation. So you actually had to dramatically reduce the energy flux transported in the simulation to still maintain a solar-like differential rotation. So it would be really interesting to redo simulations like this now with a efficient small scale dynamo if that actually improves the situation.
Thanks, that's very helpful.
Yeah. But I mean, as you know, I mean, it's very hard to diagnose directly magnetic field in the convection zone. So really the only chance to get a better handle through observation, so helioseismology is really looking at the flow signatures of convection in the convection zone, which may be impacted at some level by magnetic field, but it's only indirect. But you need simulations in the end to get the full picture and the connection.
Thank you.
Okay, Alberto, you can ask your questions.
Hi, Matthias. Thank you very much for such a nice talk. You have shown numerical simulation of a sunspot and of an Aiken sunspot. My question is, are you able to reproduce the whole cycle of life of a pore? That means a magnetic structure that never, ever develops a penumbra or penumbra-like structure.
I mean, in some sense, as I mentioned, you really, since you only get the penumbra by playing tricks with the top boundary, actually the natural outcome of most of these simulations, if you do nothing, if you just use a potential field, is that you end up with what one would call a pore on the sun.
Okay, so in that case, Matthias, my question is, even in that circumstance, in that thing that we can call pore, do you observe mode flow or moving magnetic features?
Yes.
Okay. Okay, thank you.
Okay, we have last two questions in the chat. First one by Julius Koza. Julius, are you there? Maybe I'll read it. So Julius is said he is she's happy to hear once again why we don't see a bright ring around the sunspot.
No, that is so. In this, basically, the way you can think about this is the convection zone is a two-component flow. You have upflows and you have downflows. Upflows have more or less a constant entropy until they really reach the get close to the photosphere, and you have the cool down flows, and you have some mixing in between them. What you really do in the mode region is that you change the balance between these two flow components. You have less downflows, and the reason this happens is because you have in the penumbra, you have the Evershed flow. So pretty much all the cool low entropy plasma which is forming in the penumbra is transported away from the sunspot and is drained further away from the sunspot. There are some geometric effects, like you have these funnel shape expanding structure of the sunspot, which kind of acts a little bit like an umbrella, which prevents from downflows to raining down right in the proximity of the sunspot. So you change this balance between upflows and downflows. Not having the downflows in the sunspot, that is the reason why you get the mode flow, because you also then disturb the mass flux balance. You don't have a local mass flux balance anymore. And the solution of not having a mode flow is not possible because all the upflowing plasma in the mode region is still in a pressure balance with all the other upflows in the convection zone. So it has to behave in a more or less similar way. So the only way you can find a solution with the mass flux balance is that you have a large scale overturning flow, which preferentially turns over away from the spot. There is a little bit downflows near the edge of the spot, sometimes in particular if you don't have a penumbra. But this is essentially the basic workings of the mode region. So now with regard to the hot ring, if you have this mix of upflows, hot upflows and cool downflows, and you just remove the cool downflows, then on average, the temperature will be warmer around the sunspot. That's the reason why I say you have a hot ring. But What really determines the brightness of the photosphere in the end is what is the entropy of the plasma which makes it into the photosphere. And all the upflows which are present in the mode region have the same entropy as all the other upflows outside sunspots. That's the reason why you won't see a brightness enhancement in the photosphere, because really you only change the part of the flow structure which goes downward, not the one which goes upward.
Okay, Georgius also add a comment about the ring in chat. Georgius, are you there? Do you still want to say something about this?
Sure, yeah. I was just wondering, because there is this paper by Mark Rast, I think it's obviously Nature in 1999, where they show several cases with ground-based observations of intensity, observations of sunspots. They do some image processing, I believe, or maybe some, I forget what kind of processing they do, but they bring out this bright ring around the sunspots. I wonder if this is well understood, why there's a difference between the simulation and such observations. By the way, they discuss this in the context of a conjecture by Parker, and they say that Parker was right. So I wonder if we can say now that Parker was wrong.
I mean, I think there are two things here. The one is it's really hard to do the measurement, which is really required to put constraints on whether there's a brightness enhancement or not, because I mean, as we all know, there are moving magnetic features around. There's a lot of small-scale flux enhancement in a sunspot area, which also can lead to brightness enhancement. So very often what people do is they filter a certain amount of that out to kind of focus really only clearly on, I mean, what is the brightness of granulation? But then you have to be very careful what you remove. If you remove too much, it's also not good. I mean, in some sense, you know, small magnetic fields that typically end up in downflow lanes. So you want to remove them because they just lead to a brightness enhancement on their own. But if you remove too much of this, you start removing also part of the downflow lanes, which are naturally cool, and you could artificially create a bright ring by just doing that. And I played all those games on my simulations, trying different ways to account for this. In the end, I decided the best you can do is not touch it at all, because it really depends on what you're doing. Now, with regard to Parker's prediction, I would have to look back into the paper, but I think it might depend a little bit on how you actually describe convective energy transport. If it was just described more in a mixing length type diffusive regime, then you would likely see a brightness enhancement, because you have to try to conduct kind of the heat flux around the sunspot, and so you end up with enhancement of the energy flux. But really what's different here is this idea that you really just look at the convection zone as a two-component flow system, and you just change the balance between the two components. And this idea that shouldn't lead to a brightness enhancement, that really goes back to Hank Sprout, who I think discussed this more than 20 years ago, that having these two-component flow system, you should not expect bright rings around sunspots.
And I would also comment that observationally speaking, there are some other tertiary effects that may bias the measurements. And I agree with you that it's a very, very difficult measurement to make. And what I mean by tertiary effect is actually the hot wall effect. It really depends on the mu angle you're observing a sunspot. You may be actually seeing the hot wall around the intergranular lanes, and it may be biasing your measurements because you have strong magnetic flux in between the granular lanes, and you may actually get a bias in your brightness measurements around the sunspot. So that's another possibility why this may lead to false detections in observations. So I wonder, you know, whether that's stated properly in the paper. But thank you so much for your answer. I really enjoyed your talk as well. Thank you so much.
We now have one last question in the chat from Sanjeev. Do you want to repeat your question yourself?
Yes, sure. Yeah. It was nice talk, Matthias. I don't remember you comparing penumbral filaments in your simulations with observations. So the difference that I have noticed when I have looked at observations and simulations, particularly penumbral filaments, the heads and tails of penumbral filaments in observations are more localized in terms of intensity, Doppler flows, etc., than those in simulations. So do you have any thought on what could cause this difference?
Yeah, in particular, the inner penumbra in these simulations looks also, I mean, the transition from umbra to penumbra looks more kind of fuzzy, less clear as compared to observations. And while there are some certainly enhanced flows in the heads of filaments, they are not very pronounced. And it's kind of interestingly, you know, if you go back kind of to the first simulation we ever did about the penumbra with MURaM, which was kind of one of these lab simulations. There we actually had a penumbra filament, which really very nicely showed this during the formation phase, a bright head forming with a strong upflow along the bright head, and then it was kind of propagating inward, which looked pretty much like what a lot of filaments do. It's just in that one simulation, we only had this one and not really a dense penumbra. But really, when these more large-scale full sunspot simulations, there were less examples of these pronounced heads. So the answer is, on a fundamental level, I think the simulations are capable of producing this, but if you add it all together, it just doesn't show up exactly the same way. I mean, it happens on the sun, which is slightly related to the shortcomings we have either in boundary conditions or subsurface structure we still have to figure out.
Okay, thanks.
Okay, we are actually a little bit over time. Thanks to Matthias for this wonderful presentation, and especially the very nice, detailed answers in the Q&A section. I think we have a wonderful discussion.